Hello and welcome to the Unit 4 Section 6 video on bisectors and medians. So let's start off by talking about distance and perpendicular bisectors. When a point is the same distance from two or more objects, the point is said to be equidistant from the objects. Equidistant. Which means it's the same distance, okay? Triangle congruence theorems can be used to prove theorems about equidistant points. So the perpendicular bisector theorem says that a point is on the perpendicular bisector of a segment if and only if it is equidistant from the endpoints of the segment. So the if and only if tells us that this theorem can be said both ways. You have the theorem and the converse of the theorem, and they both hold true. So what does this theorem even mean? Let's use a couple of figures to explain it. Since xy right here is perpendicular to AB and YA is congruent to YB, so we have bisected this side of the triangle, then we can say that the measure of XA is equal to the measure of XB. You can say the opposite as well. If XA and XB are the same measure, then you have a line, XY, that is perpendicular to AB, and YA is congruent to YB. So, how do we use this? Let's show some examples so you can see how this is used. Example 1. We're going to find the measure of YW. So, if we're going to do the measure of YW, well, we know by this theorem that since we have a bisector, if we're bisecting this triangle, and we bisect this side of the triangle, that the measure 7.3 here for WX is going to be the same measure as WY. Okay, so YW here is equal to XW, and XW is 7.3, so therefore YW is also going to be 7.3. Let's clean that up a little bit. YW is 7.3. And let me clean this up a little, just so you can tell that that is indeed a Y. Okay? All right, let's find the measure of BC in example 2. So here we're told that AC and BA are the same. So if BAC and BA are the same, then BD and DC are going to be the same. Well, BC is the length of the whole thing. So therefore, we can say that BC is going to be twice the length of DC. And DC being 16, we're doing 2 times 16, so therefore BC is going to be 32. For example 3, we're finding the measure of PR. Well, PR is here. RQ is going to be the same length because of the bisector here. So we can set PR equal to RQ. So PR is 2n plus 9. PQ, or RQ rather, is 7n minus 18. So we subtract 2n from each side, so that's going to give us 5n on this side. Add 18 to this side, that gives us 27. And if we divide by 5, we're going to get 5.4 equals n. Then, to find PR, we're simply going to plug that in. 2 times 5.4 plus 9 is going to give us 19.8. And so that is our answer for PR. All right, so now we've seen how it works with sides. Let's talk about what this does for us for angles. If we bisect the angle, okay? Recall that the distance between a point and a line is the length of the perpendicular segment from the point to the line. So the angle bisector theorem states a point is on the bisector of an angle if and only if it is equidistant from the sides of the angle. So again, we have an if and only if. So the theorem states that we have an angle bisector here. We can draw a perpendicular segment from PB to the bisector and a perpendicular segment from PA to the bisector. And these lengths are going to be the same. AC is going to be the same as BC. Conversely, if AC is the same as BC, then we can say that these two angles are going to be the same. So let's do examples for these. Let's find the measure of LM. Well, since this angle is the same as this angle, and this is 12.8, this also has to be 12.8. So LM here equals JM. So therefore, LM equals what JM equals, and JM is 12.8. So LM is 12.8. For example 5, we know that these sides are the same, so therefore these two angles have to be the same. So the measure of angle ABD is going to be equal to 1/2 of the measure of angle ABC, okay? Because two ABD measures, because these are the same, make the whole thing. So half of the whole thing, ABC, is going to give us what we need for one of these two angles, specifically ABD. So the measure of angle ABD is equal to 1/2 of ABC, which is what we're told is 112. So half of 112 degrees gives us 56 degrees. And that is the measure of angle ABD. For example 6, we're going to find the measure of angle TSU. Okay, so we know that the measure of RSU and the measure of TSU are going to be the same. Well, if that's the case, we just set what we're told each of these is equal to each other. So RSU is 6z minus 14, or plus 14 rather. And we know that TSU is 5z plus 23. So subtract 5z from each side, subtract 14 from each side, and we get z equals 9. But we're not done, because we're told to find TSU. So the measure of angle TSU is going to be 5 times 9 plus 23. You do that math, and that's going to give you 68 degrees. All right, moving on to the bisectors of triangles. Since a triangle has 3 sides, it has 3 perpendicular bisectors. When 3 or more lines intersect at one point, the lines are said to be concurrent. Now, the point of concurrency is the point where they intersect. The 3 perpendicular bisectors of a triangle are congruent. This point of concurrency is the circumcenter of the triangle. So the circumcenter of a triangle is equidistant from the vertices of a triangle. So using that theorem, what we're doing here is we are drawing a perpendicular segment from each side, that is starting from the midpoint of each side. So we draw all of those and we set them to the same point, or have them all meet. The point at which they meet is the circumcenter. And then we draw a line back to all the vertices. And that line that we draw back to all the vertices is the same length. So PA is equal to PB, which is also equal to PC. Now the circumcenter can be inside of a triangle, outside of the triangle, or on the triangle itself, depending on the type of triangle you have, an acute, obtuse, or right triangle. Now, a triangle has 3 angles, so it has 3 angle bisectors. So instead of bisecting the sides, now we're going to bisect the angles. The angle bisectors of a triangle are also concurrent. This point of concurrency is called the incenter of a triangle. And the incenter theorem tells us that if we bisect all 3 of the angles, which we've done here, here, and here, and have them meet at a point, if we draw a line going back to all the sides such that those 3 lines are perpendicular to each of the sides of the triangle, then those 3 segments are going to be the same length. So here, PX equals PY, which is equal to PZ. Now the incenter is always going to be inside the triangle, whether it's acute, obtuse, or right, because we are bisecting angles this time around. So this takes us to triangle medians. The segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side is called the median of a triangle. Okay, so the median of a triangle goes from a vertex and bisects the opposite side to where you have the same length on either side of that median. Every triangle has 3 medians, and the medians are concurrent. The point of concurrency of the medians of a triangle is the centroid of a triangle. The centroid is also called the center of gravity because it is the point where a triangular region will balance. The centroid theorem states that the centroid of a triangle is located 2/3 of the distance from each vertex to the midpoint of the opposite side. So in other words, here we have our 3 medians drawn, and they all meet at point P. That is our centroid. Take a look at AP here. AP is equal to 2/3 of the entire length, AY. So in other words, PY is 1/3 of it. So you can break this up into 3 parts. AP is 2 parts, PY is 1 part. And you get all 3 parts with AY. Similarly, you can say that BP is 2/3 of BZ, and for the third median, CP is equal to 2/3 of the entire line there, CX. So let's do an example for this one. In triangle ABC, AF is 9, so the length of this whole thing is 9, and GE is 2.4, so this little section is 2.4. We've got to find the length of AG and CE, so let's start with AG. Well, AG is 2/3 of the length of AF, okay? So AG is going to be 2/3 of AF, but AF is 9, so 2/3 of 9 is going to be 6. So AG equals 6. That's all you got to do. Now, we're looking to find CE next, so we're going to use this GE measurement. GE here is this part. CG is this part, okay? And we're looking for CE. CE is the length of the whole thing. So CG is equal to 2/3 of the whole thing, CE. Well, CG is CG. Actually, let me make a little correction here. This entire thing, CG, that's correct. CG is 2/3 of CE, okay? So now, let's state this. We also can say that CG plus GE is the whole thing. CG plus GE is CE, okay? Let's take this statement that we have for CG and plug it in here. 2/3 of CE is CG. So 2/3 of CE is CG. GE is here, and CE is here. Now we're still solving for CE. So let's subtract 2/3 CE from each side. So we've got GE equals 1/3 CE. Now that makes sense, right? Because if CG is 2/3 of this length, then GE is 1/3 of this length. So what we just shown was that GE is indeed 1/3 of the length of the whole thing, CE. Okay? So now GE is 2.4 and CE is what we're looking for. Multiply each side by 3 and you get 7.2 equals CE. Another way to look at this, let's just look at this segment here. CE, C here, okay? And we've got G right here. This is 1/3 of it. This is 2/3 of it, okay? If we know that GE is 2.4, that's one part. We know that this has got to be 2 times 2.4. The whole thing has to be 3 times 2.4. And that's for the whole thing. And that's what we ended up doing here mathematically. 3 times 2.4, 7.2. They gave us the length of the whole thing. So it may be more helpful if you look at this more visually like this. All right. Let us take a look at the last topic. One last side note before we wrap up this section and this unit. And let's talk about altitude, because this will be popping up again in a couple of units. So let's go ahead and get this vocabulary down now. A perpendicular segment from a vertex to the line containing the opposite side is the triangle's altitude. And altitude can be on the inside, outside, or on the triangle itself. Okay? So if we have an acute triangle, our altitude is typically going to be on the inside. If we have an obtuse triangle, then it's going to typically be on the outside, because the altitude is just the triangle's height. How tall is the triangle? Here, for a right triangle, it is basically on the triangle itself. Okay? So just a little bit of vocabulary to take away here at the very end of this unit. All right, that wraps up this unit on triangles. Coming up in the next unit, we will be talking more about triangles and a topic called similarity. That's going to be the bulk of what we do in Unit 5.